the others. It's maybe a little bit more based on theory. So everybody's had wonderful applications and pictures and you know, really sort of dynamic talks. So you'll have to forgive my my lack of pictures. So I guess there's one at the beginning, but it's stolen from someone else. So anyway, okay. So because we've seen so much on peridynamics so far, I won't focus too much on the model and where it comes from. But I will say that the way that I'm writing the balance law for the equation of motion in time is in this way, where capital lambda is the mass density, and then U is written as the displacement, and then L is the is an integral operator that's associated to the linearized bond-based peridynamic formulation. And so there's the picture, but it's been stolen, so it isn't really mine. Anyway, so the motivation is again, this is the bond-based linearized model or a formulation of it. So everything that we'll be describing, because this is a talk on theory, what we were able to prove. What we were able to prove is really based on is globally posed, so equations posed on all of RD, and so everything is globally defined. However, you can take the kernel rho here, or the influence function, to be something with finite horizon. So you can take that to be compactly supported. And so the oscillatory system that we're talking about is we're motivated based on looking at the peridynamic formulation in heterogeneous media, and we're interested in looking at short range forces on the scale of those inhomogeneities. So in the peridynamic force, and so we're following some of the precedent that's been set. It was first set by Basim and Rob in 2012, and there's been a number of papers based off of their formulation. We consider the mass density to be dependent both on both spatially dependent and it varies based on the length scale of the inhomogeneities, as well as the parameter beta as well. And so the balance law on the previous slide can be rewritten this way, just by dividing by the mass density. And so then we take this here to be an operator that depends on x and epsilon, and then the external load to depend on epsilon as well. Whoops. Don't know what happened there. Anyway, so in this case, so we've rewritten this as such, and so what we were able to prove was for the time independent problem. So we were able to prove some things for, so this should just be x. T shouldn't be there, but we consider the time independent problem, or the static problem, and then we look at the convergence properties of the solutions as epsilon goes to 0. So convergence meaning a sequence in epsilon. And so the thing is that, like I say, everything is globally defined, and what we were able to prove was a statement about so the operator L epsilon turns out to be non-negative definite in L2. But since everything's globally defined, we were able to prove something about the positive definite operator. So in addition, hence we add an M here, which turns this operator into something positive definite, so long as M is positive. And so that's what we do. We consider if you have if your external load is in L2, what happens to the system as epsilon goes to 0. And so the L epsilon is a rewriting of the motivational formulation that I had on the previous slides. And so we're interested in seeing what happens, what's the effective behavior of this system. So here, here we have lambda, which is the reciprocal of the mass density, It's assumed to be smooth in X, and then both lambda and beta are periodic with unit period, hence the rescaling here in epsilon. And then what we also do is consider what happens in the event of a vanishing horizon as well. Okay, but we don't exactly write it as a vanishing horizon. We write it with an extra diffusive scaling as well. So the thing is still posed on all of RD, but again, if rho is compactly supported, this is the equivalent of this is equivalent to a vanishing horizon if rho is compactly supported. And so if you'll notice, we're considering the horizon vanishing on the same length scale as the heterogeneity. So we're considering sort of two different regimes that are coupled together here. And so what we'll be able to show is that the solutions U epsilon are converge to a function where U solves a local elliptic system of equations that's related to the or closely resembles the Lemay-Navier equation. So let me just say a little bit more about the scaling here, about the scaling in epsilon. So in the absence of diffusive scaling, that is, if there's no epsilon squared here, the effective behavior can be seen to be characterized by a system of non-local equations. So you have some effective non-local equations. So results. I mean, at least so results related to these, at least considering this regime, results in this regime are found in Nassim and Rob's paper in 2012, as well as considered by Chung, Rob, and Tadella in 2016, and then a different formulation, but still, in this regime was considered by Tadella and Chung in 2015. Now, in the absence of the heterogeneity, in other words, if the terms in red here are identically one, then you are in the regime of vanishing horizon. So you're looking to see what happens as the horizon goes to zero, and so that's in effect localizing the equation. And so you can see via either a formal argument or using gamma convergence that asymptotic behavior is characterized by the Lemay-Navier equation in classical linear elasticity. So this was done by Emmerich and Wechner in 2007, and by others since, and it's since been seen in several different contexts. But those are the two regimes that we're considering, and so we're considering them simultaneously. So that's sort of what our main interest is. So again, this is what we're able to prove. It would be much nicer maybe to consider a problem like a variational problem stated on a bounded domain, or something like the state-based model. And this is work that's ongoing, but this is what we're able to prove so far. Okay, so here's the result. It's a result about we're able to prove that solutions converge in L2, where U epsilon is a solution to the positive definite operator associated to this peridynamic formulation in the case of heterogeneities, and so those converge to U0, where U0 solves a classical second order local differential equation. And so the form of that local differential equation is closely related to the Lemay-Navier equation, or at least its form is. So it's equal to an operator non-divergence form whose fourth order tensor is elastic and infinitely differentiable in X. So what do I mean by elastic? I mean it satisfies the Cauchy relations, the symmetries that the classical fourth order elasticity tensor satisfies in linear elasticity. And it is also coercive and continuous with respect to symmetric matrices. So it satisfies a special type of Legendre-Hadamard ellipticity condition, which is exactly what the elasticity tensor satisfies. And so its particular form is that it's equal to actually a constant depending on or it's equal to a function of x times a constant tensor. And so the form of this constant appearing here in x closely resembles what you see in classical local elliptic homogenization problems. So that is the inverse of some averaging of the inverse of your coefficients. And so this form is something that's expected, and it depends on lambda. And then the constant fourth order tensor, the C tilde, depends on beta and rho. But it is still constant. It depends on somehow the moments of beta, which was the parameter, and then the influence function or kernel rho. Okay, and so the way we do this is the asymptotic analysis we use is corrector methods, and this has been done for sort of similar methods have been used for non-local scalar equations, and sort of the first one was by Biednitsky and Legendre in 2017, and so there's been a lot of work done since then on non-local operators that have this sort of simultaneous on the connection of homogenization regimes and representing the short range forces as well as the vanishing horizon. Okay, so some of the conditions on rho. So we don't assume that rho is radial. Again, we're trying to prove things, so we're trying to prove them in sort of as generally as possible. So in particular, peridynamic kernels or peridynamic influence functions, that are radial work, but we can be a little bit more general. And I should say that all of this is done for integrable kernels, so kernels that belong to L1. And so, but the thing is, we only need that the function is even. It doesn't need to be radially symmetric. However, it does need to have. It needs to be in L1, and its second moment on all of our DLs needs to be in L1. And so, but the thing is, it doesn't need to be supported, on a ball near the origin. It can just be supported on a cone with vertex at the origin. So it can degenerate. So if it is radial, then it can degenerate on some subset of the sphere. It needs to be supported somewhat at zero, but just on a cone. So there's a very general set of influence functions that one can consider, and you'll still get a similar result. Okay, so if I should say also that in the absence of the inhomogeneities, we recover results that already exist in the literature. So if indeed rho is radially symmetric and the parameter beta is just identically 1, what you see is that you get a Lemay-Navier equation with the Lemay constants, the Lemay constant mu equal to this function here, where it corresponds to the Lemay constant mu, but but in this case it depends on x. So that's the form that you get, and that's again something that's expected. This has been done in the case of constant coefficients. That is, if beta is identically 1 and lambda is identically 1 as well. So so we recover what's already there, what's already in the literature. So I do want to say that just to see what we're talking about here is that certainly the solution, we're talking about solutions converging to another solution, and so that solution set is indeed non-empty. There exist solutions to the limiting equation, and that is well known using classical techniques. And then so that means that the resolvent is a well-defined bounded operator. That is, the data to solution mapping the data F to the solution U is well defined. And again, standard regularity theory gives you that if the data is smooth, then so is the solution. So the limiting operator has a well-defined solution set. That is, the inverse operator is well-defined. And so the resolvent operator, the associated to the non-local equation for each epsilon, for any fixed epsilon, is also well-defined. And that turns out to be, it turns out that the operator L epsilon, because the kernel, the influence function is in L1, this operator is bounded from L2 into L2. And so the resolvent operator is indeed an isomorphism from L2 to L2. So that means there exists some constant. So the resolvent operator, the data solution map acting on the data is bounded by the L2 normative data. Okay, so both the resolvent for the limiting equation and the resolvent for the equation m minus L epsilon is well defined. And so you know, because this is really an analytic result, I'll just sketch the proof. So this is just a sketch using the corrector technique. So the idea is to find some ansatz, some perturbation of the limiting solution U, so that when you plug it into L epsilon, that is you know, that is relatively close to the limiting operator acting on the limiting solution. So so the ansatz is here, and so the main point is that we have to be able to solve for these correctors here, the function A and B here, depending on x over epsilon. And so we can do that via the associated cell problems. And so what we see is that indeed L epsilon, W epsilon is equal to this expression here, where the psi A and phi B depend on both the, well, psi A just depends on the corrector A, but then this the second order function also depends on both A and B. That's the point of showing this. And so here's the point is that both of these, so we want L epsilon W epsilon to have this form, and so indeed you know, what we want is that we want this function here to be 0, and we want this function here to be the limiting equation. We want, or the limiting operator, and so that gives us associated cell problems that turn out to be solvable so long as we have the proper conditions on rho. And so let me just skip ahead here to show that indeed that indeed the ansatz here with L plugged into L epsilon, as epsilon goes to 0, if you subtract this c of x times the second derivative of u here, this indeed goes to 0. And of course, because u of x is some expansion in terms of epsilon, then w epsilon minus u will also converge to 0. And so the whole point is that you know, the fact that this happens is because we have very particular forms of these terms that show up when you plug this ansatz into this equation. And so we actually get that this is equal to 0, and that this is equal to my second order tensor, or my fourth order tensor times times what turns out to be the Hessian of the limiting solution. So and so again so again really the meat of the proof here is solving these equations for capital A, and then substituting that, and then you get an equation that you can solve for capital B here. Okay, those are the cell problems that can be resolved using Fredholm theory, among other things. Okay, so I did just want to put a proof in here for why why this ansatz does the job for us. And so again, the goal is to show that U epsilon solves my approximate my peridynamic equation, that U0 solves the limiting guy. So we want to show that goes to 0. So you can use the triangle inequality pretty easily. The thing is that you know that that because the classical theory tells us that U0 is small enough, or smooth enough, we can define the ansatz relatively easily, and so then we get that that U0 minus the ansatz converges to 0, and so then what you have, you use the triangle inequality and the fact that V epsilon converges as epsilon goes to 0 to L0 U0. And so again, I just wanted to put the sketch up here, and so but just for the sake of time, so that there's time for questions. I know I started a little late, but it's okay. But the idea is really basically the triangle inequality and application of the result. So like I said at the beginning, this is sort of in a very idealized setting, and so we'd be really interested in trying to do this for more general inhomogeneities, or to try and treat a more general a boundary value problem, rather than just showing convergence of operators that we can invert. We'd really like to see an application to problems in the literature. And then, as well as, we were also interested in finding an analogous result in the dynamic setting. So we go back to the beginning really quick. And so what I want to point out is that, because we divide it out by lambda here, in some sense, but then we consider the time-independent problem. In some sense, we didn't need to consider this lambda at all. However, if you're in the time-independent problem, that lambda doesn't go away. So we tried to develop the theory in the sort of elliptic time-independent case, so that it could easily be adapted for the associated wave equation. So that's what our interest was, and so that's what I have. Thanks very much for your attention.